two vocab words that we had gone over were end, behavior, multiplicity. Let's actually, you know what, pause on what these ideas are. I'll come back and chat about those when we get to the next page. But the first thing that we went over are how we name a polynomial. So remember that a polynomial is classified based on its largest exponent, which is the degree. That's the polynomial's first name. And then it's also classified by the number of terms. Okay, so the number of terms, terms are separated by plus or minus signs. And then based on the number of terms, we get to the last name. So part of what I want us doing is just thinking about some of these words and how that relates to us building an equation around that. Okay, so all we're going to do is write a polynomial based on the description here. So I need to write a trinomial, meaning 3 terms, with a negative leading coefficient. Okay, so remember that leading coefficient, we did define that. That's the coefficient of the highest degree term. So just some negative number. And then a degree of 4. Now, there's lots of freedom here, right? The description is not very specific. We just need to see these 3 things. So when you're writing these polynomials, because your homework is going to have similar questions to this, you're going to have, we could all come up with something different here. Okay, we're not going to all come up with the same thing. Okay, so here's what I would think about and what needs to show up. Okay, so a degree of 4. So my first term, I'm going to make it x to the 4th. Okay, that takes care of the degree of being 4. The negative leading coefficient, well, this is going to be my leading coefficient, whatever I put in front of the x to the 4th. Let's make it negative 3. It could have been negative 1. It could have been negative 0.1. It could be anything. Okay, as long as it's negative. Okay, so we took care of the negative leading coefficient. Then a trinomial. So we need 3 terms. I only have 1 right now. So there's lots of things I can put after this, but we need to make sure we're putting things that don't combine to get to one single term. So let's do like plus 2x and then minus 7. There's our 1, 2, and 3 terms. Okay, so the only thing that needed to happen were 3 terms, degree of 4, and negative leading coefficient. All right, why don't you all come up with something for number 2 based on the description. I'll tell you what I come up with and what needs to for sure show up as you go ahead and build those equations up. And the first one in number 2 here, so a cubic polynomial. So whatever you write, the largest exponent needs to be a 3. Then, since there's 4 terms, you need to have an x squared, an x, and a constant term. What coefficients you put in front of that can be anything. It doesn't matter because the description doesn't say it. Okay, but for us to have 4 terms in a cubic, each term needs to have a different exponent. Okay, otherwise they would combine and simplify and not be a 4th term or 4th term polynomial. Then the leading coefficient is positive and a fraction. So again, any positive fraction would work there. Okay, it doesn't need to be the exact same as me. So need to see the cubic, need to see 4 terms that cannot combine at all, and then a fraction positive leading coefficient there. All right, and then 3, 7th degree binomial. 7th degree means the largest exponent is 7. Binomial meaning only 2 terms. Okay, so you could put x to the 6th, x to the 5th. It doesn't matter. Okay, the second term can be whatever you want it to be. And then an even leading coefficient, so the number in front of the x to the 7th, some even number. Cool? All right. Go ahead and flip the page. Oops. All right. So next thing we're going to talk about is the end behavior of a polynomial. The end behavior is what happens to a graph when we go all the way left, okay, to negative infinity, or all the way right to positive infinity. With polynomials, one of 2 things is going to happen. The ends are either going to go up or down. So I actually like to start this out by reminding you of 2 equations you know well. Okay, so if I have y equal to x, okay, that's a linear function. Okay, if I were to graph y equals x, first off, this is a polynomial. Okay, we've worked with polynomials. You had a whole unit on linear functions. Okay, this graph looks like this. Okay, so this is showing me that the right end, the right is going up, and the left end is going down. Okay, because as we go all the way left to negative infinity, this end just continues down to negative infinity. The right end, as I go positive, goes all the way up to positive infinity. So the ends are what happens as we go all the way left and all the way right. So to negative and positive infinity. The other graph that you know well is x squared, right? We literally just took a test on our quadratic unit, okay, where the graph looks like this, okay, the parabola. In this case, the right end is up, the left end is also up, okay? So as I go all the way left to negative infinity, the end is going up. As I go all the way right to positive infinity, the right end is also going up. Okay, so with polynomials, those are the only two options. Okay, the right end going up or down and the left end going up or down. So there's essentially, what would that be? 4 combinations of how these can play out. Okay, and there's 2 things about a polynomial that will determine what happens with our end behaviors. So first, the degree. Okay, when the degree is even, the ends go in the same direction. Let's make a note of that. So even, ends go in same direction. Okay, like the x squared. Okay, that's an even degree. 2 is even. Both ends are going up. Okay, so for an even degree, both ends are either both up or both down. An odd degree, like a linear function, is just the opposite. One end up, one end down. So ends go in opposite directions. Okay, we'll say opposite directions. Okay, so no matter what degree, if it's odd, one end is up, one end is down. So here's kind of the trick that helps me memorize all of this. Okay, because there's 4 different ways of how these can play out. The leading coefficient, okay, whether it's positive or negative, tells us the right end. Okay, so that leading coefficient will always dictate what happens with the right end. Okay, so here's when and we're going to go through some examples here, but if I'm looking at, come on, focus. If I'm looking at a polynomial with a positive leading coefficient, that tells me the right end is up. If it's negative, that's telling me the right end is down. And then we're back to positive, so up again. And then negative, down again. So that's where I start. Okay, when I'm determining whether a polynomial, its end behaviors are up or down, I look at the leading coefficient. If it's positive, it tells me the right end is up. If it's negative, it tells me the right end is down. Then I use the fact of whether the degree is even or odd. So if my degree is even, my left end just matches what I did with the right. So in this case, since the right was up and it's even, that means the left is also up. Okay, if I have an even degree, but it's negative, so the even means the ends go in the same direction. We already determined the right was down, so now the left is also down. Okay, then if it's an odd degree, I know the ends go in opposite directions. So if I have one that's up, the other will go down, and vice versa. So I already found the right was positive, or the positive coefficient tell me the right is up. Since they're opposite directions, tells me the left needs to be down. Okay, and then just the opposite here. If our leading coefficient is negative, the right is down. It's an odd degree, so the left is up. So I should say left. Left. Okay, so here's how we'll write those. You don't need to write the left or right. I know when you do this, you're saying the left is up, the right is up. Okay, negative, even, down and down. I know that you're telling me the left is down and the right is down. Okay, down then up. I know you mean the left is down, the right is up. Up and then down. I know the left is up and the right is down. So you don't need to write left to right. The left arrow is the left end behavior. The right arrow is the right end behavior. Okay. All right. So just some examples. And again, to help, like every year, students act like this is a hard thing to memorize. And there's a lot that goes into it. I get that. One way to kind of help with that is just think about any graphs you know well. Okay. So a positive even degree, well, that's what we just drew, like an x squared. Okay. A parabola. Okay, this is x squared. Positive leading coefficient, even degree. Okay, even degree negative leading coefficient, well, how about negative x squared? Where it just flips. Okay, then an odd, let's actually use x cubed, although we could use just x like I kind of did at the beginning here. An x cubed, the graph looks like this. I guess we did have that parent function unit where we've seen this before. So the right side is up, the left side is down. And then negative x cubed, that just reflects that graph. So now the left is up and the right is down. Okay. So now we're going to look at some equations and determine the end behavior just by the actual functions. Question first, though? So for these, we're going to describe the polynomial. We're going to identify, you know what, let's name it. I don't know that the direction was great. Let's name it. Identify the leading coefficient, the degree, number of terms, and end behavior. Okay, so it helps if we know the degree, because that's part of the name. So the degree here is 3. That's the largest exponent we see. The leading coefficient is the number in front of the highest degree term. Okay, so the highest degree term is x cubed. The number in front of it is a positive 1. The number of terms here. Those terms are separated by plus or minus signs. So there's 1, 2, 3, 4 terms. Okay, so this gets us to our name. So this polynomial would be named a cubic for the degree of 3. And there are 1, 2, 3, 4 terms. So it's a cubic polynomial with 4 terms. We don't have a name after 3. So it goes monomial, binomial, trinomial. So a cubic polynomial with 4 terms. So it's got a long last name, polynomial of 4 terms. And again, the two things that go into that, number of terms and the degree. Now for the end behavior. Okay, and this is where we want to listen carefully because I've got a way where we don't need to memorize that table at all. I'm first thinking about the right side. And the right side is based on the sign of the leading coefficient. Since the leading coefficient is positive, that tells me the right side is up. The left side, I just think about the even or odd idea. Okay, if they're even, both ends go in the same directions. If they're odd, they're going to go in opposite directions. This is an odd degree, so that means the ends need to go in opposite directions, making the left end down. So odd degree, the degree is 3, means ends go in opposite directions. Positive leading coefficient tells me the right side is up.
How can you tell that the leading coefficient is 3?
It's positive 1. It's the number in front of the x cubed. That's a positive. Yeah, that's supposed to be a plus. Yeah. Yeah, so the leading coefficient, number in front of the highest degree term. Okay, let's do one more together, and then I'll have you all do the next two. So number 5 here, the degree, and we know this well, this should be familiar. This is a quadratic, so degree of 2. We have a leading coefficient that this time it's negative 1. Number of terms. 1, 2, 3 terms. So we can name this as a quadratic trinomial. Okay, so the degree of 2 is how I got the quadratic. The terms of 3 is why it's a trinomial. And then the end behavior and I'll pause a sec so we can listen to my thought process for the end behavior again. So again, I think about the right side first, as the right side is dependent on what the leading coefficient is doing. Negative leading coefficient tells me the right side is down. Even degree means the left end goes in the same direction as the right, so it is also down. So this end behavior are both ends going down. And again, that one's a little bit easier to visualize because we've worked with quadratics. Okay, that's going to be an upside down parabola. Okay. All right, everyone do 6 and 7. Okay, do they identify the exact same things? You know what, even do the graphs. See if you can think about what those graphs are going to do. Right below it. We'll talk about all of them. I'll give you a few minutes to. 6 has a degree. That is 5. Again, that's just your largest exponent. Leading coefficient is a positive 1. The term numbers, there are 3 terms there. So the 5th degree makes this a quintic. The 3 terms makes this a trinomial. The end behavior, the right side is up because of the positive leading coefficient, and the left side is down because it's an odd degree. So one end is up and one is down. Since we already found the right to be up, the left has to be down. All right, for 7. The degree is 6. Again, that's your largest exponent. Leading coefficient is -1. It's the number in front of the x to the 6th. There are 1, 2, 3, 4, 5 terms. The name, it doesn't have a great name here because we're kind of past the threshold of where we start to get lazy. So just the 6th degree polynomial, more specific 6th degree polynomial with 5 terms. And then your end behavior, the negative leading coefficient telling me the right side is down. The even degree telling me the left side is going in the same direction, so also down. So down and down. All right, questions with how I'm identifying anything on 6 and 7? Yeah. Yeah, I'll get to the graphs in just a second. Okay, but questions on anything I did with 6 or 7 here? Okay. All right, now to the graphs. Okay, so if I give us a graph based on what we just talked about or some of the vocab we came up with, we should be able to look at the ends and decide if it's an even degree polynomial or an odd, and then what the sign of the leading coefficient is. That is going to become really handy as we have a lesson coming up where we're going to try to write the equations of these graphs. Okay, and starting with that is a really helpful thing. So I'm noticing this right end is down. So that tells me the leading coefficient is not positive. I messed that up. That should be negative. Okay, with the right side being down. And since both ends go in the same direction, it's even. Okay, an even degree. The other graph, that right end is up, so it's a positive leading coefficient. One end is up, one is down, so it's an odd degree. Yeah. Just the sign. We don't know the value of it. It could be positive 2, it could be positive 3, it could be positive 1 million. We have no idea. We know it's positive though. So yes, it tells us the right end. Okay. Go ahead and flip this page over as well. Okay. And let me get voices to stop again, please. Shh. All right, so we won't do a ton of this today. This is going to apply more tomorrow, and I'll revisit this same idea tomorrow. But really helpful if we kind of have this idea already in our brains before we start. We're going to start graphing functions tomorrow, at least sketching them. So having this down can be really helpful for that. So first off, the equations didn't print well because of it was in the wrong format. So Go ahead and just rewrite them. This is x minus 1, and then x plus 1 to the power of 12. Okay, I made that a little ridiculous. And then this next one, let's call it 5x, x plus 2 squared, and x minus 3 cubed. And I'll give you a sec to write those down. So multiplicity, the definition, which we defined on the front page as well, is just how often a solution occurs. Well, you might be like, how can a solution show up more than once? Okay, what does that even mean? Okay, so here's how I kind of introduce this. I start with, again, something we know really well. Okay, we know x squared really well. Okay, so if I told you to find the solutions, that would mean we let y equal 0, and we're solving for x. Now, what is the actual x value here that makes it 0? It's just 0. Okay, but this equation has how many solutions? 2. So if I'm like, hey, I get 0, the 0, can it be plus or minus? 0 can't be plus or minus, right? So if there's 2 solutions, but we're only getting 0, what does that mean? Well, here's another way to write x squared. X times x. Wouldn't you all agree x times x is x squared? Well, if I now take each factor and set it equal to 0, I'm getting 0 to show up twice. Okay, so 0 is both solutions, okay, of this quadratic term. That's going to eventually tell us what happens at those x-intercepts. Okay, so multiplicity is how many times we get a solution. It is dictated by the exponent on that corresponding factor. And let's definitely underline that. If you have a highlighter, maybe even highlight that. Right, so when I look at x squared here, I'm like, hey, the solution is 0. The exponent of 2 means that I have that solution twice. Okay, so in this table, what I like about it is we're really having to think about all of the vocab here. Okay, so list of zeros and the multiplicity of each. If I set x minus 1 equal to 0, what's the solution there? Just 1. Okay, so I get a solution that's 1. If I set x plus 1 equal to 0, what's the solution there? Negative 1. So now, every solution has a multiplicity. Okay, the minimum multiplicity a solution can have is 1. But then, the number of times it shows up is equal to the exponent on it. Okay, so this solution of 1 has a multiplicity that is just 1. Okay, x plus 1 to the power of 12. We're going to get this negative 1 12 different times. Okay, it has a multiplicity of 12. And again, that's because it's x plus 1 times another x plus 1 times another x plus 1 12 different times. So we're going to get negative 1 to show up 12 times. Now let's skip the leading coefficient. We'll come back to that later because it's a little more complicated. The degree, and this is where it starts. I start to get students confused. It's the largest exponent, but when everything's multiplied out, these equations are in what form? Factored form, so they're not in the standard form. Everything we did on the front page of these notes was all in standard form. So if we want to find the degree of the polynomial when it's in factored form, anybody have an idea of what I do with the exponents? We just add them, but it would be if we FOILed. Okay, so we would get the degree if we FOILed all this out. Do you know how long it would take us to take x plus 1 times itself 12 times? We could start right now. We may not finish by the end of the school day. Okay, I don't want to do that. Okay, so when it's in factored form, you have to add the exponents on the x's. Okay, so our degree here is 12 plus 1, which is 13. Okay, this isn't a great example. Like usually I would actually multiply it out and we could see that happening. But again, multiplying out something to the power of 12, it would take us way too long. Okay, so when in factored form, the degree is us adding the exponents or the multiplicities, right? Multiplicity of 1 plus 12 should match what we're calling the degree, which matches the number of solutions we have. Okay, so let's do this next one. 5x. If I set that equal to 0, what's my solution? 5x equal to 0, it's just 0. 0 divided by 5 is 0. X plus 2, if I set that equal to 0, I get negative 2. X minus 3, I get x equals 3. So the solutions are what values make the factors equal to 0. The multiplicity, or how often that solution shows up, depends on the exponent on these factors. So the x only has an exponent of 1, so its multiplicity is just 1. The x plus 2, well, that means x plus 2 times another x plus 2, so we get negative 2 to show up twice, and thus it has a multiplicity of 2. 3, I'm going to get that to show up 3 different times. Okay, because of the cubing. That's like an x minus 3 times another x minus 3 times another. So then the degree here is us adding all of these together. So 1 plus 2 plus 3, which is 6. So the multiplicities equal the degree, which equals us adding all the exponents. Okay, so remember, and we'll talk about this throughout the whole unit, your degree is going to be different on how we find it when it's in standard form compared to factored form. Yeah? Yes. Because it's just like we're just counting how many times we get the solution, we've got to get it at least once, and we can't get a solution negative times. Yeah, that's a great question, though. Okay, so last little thing we have here, and this is going to relate more to what we do tomorrow, and I'll remind us about all this tomorrow, is the multiplicity of a particular solution tells us what that graph does at the solutions. So when I say solution, what point am I referring to on the graph? The x-intercepts. Okay, so x-intercepts are the solutions. Okay, so there's two behaviors we need to know. If we have an even multiplicity, the graph bounces, meaning it touches the x-axis and then stays on the same side. Okay, think of it touching the x-axis and bouncing right back where it came from. Odd multiplicity, it's just going to pass through. So if we start below the x-axis and we have an odd multiplicity, it's going to pass through and go to above the x-axis. Okay, so as the multiplicity increases, so as we go from like 2 to 4 to 6 to 8 to 10 to 12, then we just kind of pause and hang out around that x-intercept for a little bit longer. Okay, and same thing with like a pass-through. If we go from 1 to 3 to 5 to 7, we just end up hanging around that x-intercept for a little bit longer. Okay, and I can pull up some graphs to show that when we actually start graphing tomorrow. All right, so here's what I mean by it. Okay, y equals x. That means we have a solution that is x equals 0 with a multiplicity of 1. Well, we know this graph well, right? It's just a line. But here's what I mean by my solution. That means I have an x-intercept at 0. The multiplicity of 1 tells me I pass through. To pass through, I'm going from one side of the x-axis to above it. Okay, so this is what I mean by a pass-through. And then x squared, the solution, once again, is x equals 0, but now has a multiplicity of 2. So we're going to bounce at that x-intercept. Okay, so I start at 0. Or I have my x-intercept at 0. The left end is up. I'd come down. I'd touch that x-axis, and I'd bounce right back up. Okay, so this is what I mean by bounce. And again, we'll talk more about that tomorrow. So we'll reintroduce all these ideas then. Yeah.
So the bouncing is always like automatic.
It's not